Hello friends, welcome to my channel. Let's have a look at problem 545, boundary of binary tree. In this video, we are going to share a treatment based on traversal. Here we are going to use different kinds of traversals to glue the left boundary, leaf nodes, and right boundary together. First, let's look at the problem statement. So the boundary of a binary tree is the concatenation of the root, the left boundary, the leaves ordered from left to right, and the reverse order of the right boundary. So notice that we are going to reverse the reverse order of the right boundary. So this is very important. Another thing is that this problem distinguishes the root with respect to the left boundary and the right boundary. So let's look at the definition of left boundary in the sense of the current problem. So the root node's left child is in the left boundary. If the root does not have a left node child, then the left boundary is empty, right? So if a node in the left boundary has a left child, then the left child is in the left boundary. The third one is that if a node is in the left boundary and has no left child but has a right child, then the right child is in the left boundary. The leftmost leaf is not in the left boundary. So this is an important point, right? So the right boundary is similar to the left boundary, except it's the right side of the root's right subtree. Again, the leaf is not part of the right boundary, and the right boundary is empty if the root does not have a right child. The leaves are nodes that do not have any children. For this problem, the root is not a leaf. So this is also an important point. So the overall requirement is that given the root of a binary tree, return the values of its boundary. So notice that there are two examples. Let's examine them with some detail. For example, in example 1, the return is 1, 3, 4, and 2, right? So the left boundary is empty because the root has no left child, right? The right boundary actually is following the following. The right boundary follows the path starting from the root's right child, right? 2 and 4, right? So actually this one is very special. So if we use the same convention as the left boundary, so we shouldn't count 4 in the right boundary. But this is a treatment detail we can control in our code. So the leaves are 3 and 4, right? So so the root, left boundary, leaves, and right boundary, right? So similarly in example 2, so we have a root that is 1, and the left boundary is 2 and 4. And 4 is not belongs to the left boundary. So to correct, so 1 is the root and 2 is the left boundary, and then 4, 7, 8, 9, 10 are the leaf nodes, and 6, 3 are the right boundaries. So however, when we write the code, so we can actually get all of these parts, right? So we just need to exclude the leaf, right, in the left boundary, in the very left boundary, in the traditional sense, right? So with that said, so let's also look at the constraints for this problem. So first, the number node in the tree is in the range given by the closed interval, so 1 and 10 to the power 4. So this says that overall the tree is not null, and the number of nodes is bounded above by 10 to the power 4. The number 10 to the power 4 gives us an upper bound for the problem size. And the second constraint is that the node value is in between -1000 and +1000. So in particular, the node value can be 0 or negative. So with that said, we are ready to do the analysis. So here we are going to use traversal to glue the left boundary, leaf nodes, and the right boundary together. So our plan is the following. We are going to write 3 hyperfunctions to achieve the following 3 tasks. first we want to get the left boundary. So here we are going to mimic the pre-order traversal. In the second, we're going to get the leaf nodes. We're going to mimic the in-order traversal. And the third one is get the right boundary. So we are going to mimic a traversal order is right plus left plus root. So let's turn this order as reverse post-order traversal. So here is an important note. So when we do the coding, we need to avoid repetition. For example, we need to avoid the node that is both in the left boundary in the traditional sense and is also a leaf, right? So in the sense of the current problem requirement, so the very left child is not in the left boundary, right? So this part is important. We need to treat this case when we write the code. Similarly, note that is both in the right boundary and in the traditional sense, and is also leaf is not in the right boundary in the sense of this problem. So let's look at some illustrations before we write the code. So let's first look at the left boundaries. So this is going to mimic the pre-order traversal. So this is the tree, right? So if in the traditional sense, actually 1, 2, 3 are the left boundaries. So however, we do not count the root, and also we do not count 3, right? So in other words, in this problem, 2 is the node in the left boundary. So in this problem, so if we use this the definition in this problem, so the left boundary is empty because the root has no left child, right? So this actually is according to the first atom. So in this third one, so we have 1, 2, 3. So in this tree, so in the traditional sense, so 1 and 2 are in the left boundary. However, we do not count 1, the root, and also we do not count the leaf. So in this case, the left boundary is also empty. However, the overall return for this one is 1, 2, 3, right? We have root and we have 2 leaves. So in this problem, so the left boundary is also empty because the root has no left child. So this actually mimics an incomplete pre-order traversal in our code. So now let's look at the leaf node. So this is actually very simple, right? For example, here 2 and 3 are the leaves, and in this example 2 is the leaf, and in this example 3 is the leaf, right? So this is going to mimic an incomplete in-order traversal. So let's look at the right boundary. So in this case, so actually we do not have a right boundary. So because here is a root, so here is a left child, so we do not have right child. So this tree, so in a traditional sense, 1, 3 are the right boundary, right? So here I mean red in this part. So but 1 is the root and 3 is a leaf. So in this sense, the right boundary is empty. So in this problem, in this example, the right boundary using the problem order is 4 to 1. So this is in the traditional reverse sense. But in the problem requirement, 1 is not in the right boundary, 4 is not. So we have 2 here. So with that said, so we are ready to look at the code. So we hope that we have gained enough intuition to write code with ease. So I'm going to write some hyperfunctions. So this functions is going to help us get the left boundary, the leaf nodes, and the right boundary. So here at the very beginning, so we're going to define. So first, let's maybe first define this function. So this function is going to modify a predefined list, right? So I'm going to call that list say boundary, right? So just to make that the overall logic is clear. So first I'm going to define DFS. So let's see the leftmost. So I'm going to left. So in this case, because in the definition of this problem, we are not going to include a the leaf node. But now, for now, let's first include the node, the root, so that we can write it with some convenience, right? So if not node, and so if not node left, and not node right. In other words, if the node is null, or if the node is a leaf node, we are going to do nothing, right? And otherwise, so we are going to add the value of this node to the boundary, right? So we're going to use, so let's use this boundary. So we're going to append node value, and then we're going to check left, right? If node left, what we're going to do is call this function df node left. Otherwise, so we're going to call it for the node right. So this corresponds to the items here. This two, right? This node check here is corresponding to the fourth bullet item, right? So this is the first function, right? And now let's look at the second function. So we're going to call it dfs leaves. So we're going to accept a node, and then first if not node. So what we are going to do is nothing, right? We're going to do return. Otherwise, we do dfs leaves node left, and then we're going to check, right, if node is not root, right? And so it's a leaf, so let's check it's a leaf. So it's not node left and not node right. So in this case, so we're going to add the thing, the node value to the list we're going to initialize. So next we're going to call this if node right. So this is the second function. So this is going to help us get the nodes, the leaves. So also these leaves are not the root. So the third one, let's see, dfs, we're going to call it right. So we're going to get the right boundaries. So if not node, or it's not a leaf, not node left, and not node right. So in this case, so either it's null or it's a leaf, so we're going to return. Otherwise, so we're going to try to do something to modify the boundary. So what we're going to do, we are going to first check the right in reversal. So let's, as we mentioned, we are going to use right, left, and root. So here, if right, we have right subtree. So what we're going to do is dfs right. So we're going to do node right. Otherwise, so we're going to dfs right, node left. After we did right, left, then we're going to do boundary append node value. So this is the three hyperfunctions, right? So once we finish this, so we can regard them as workers. So what we can do is to do the problem logic. So first, if not root. So actually, we do not need to treat this case because the root, the tree is not null. So let's delete that. So let's call boundary. Let's denote this boundary. So we're going to have root value. And then first, I'm going to get the right, the left boundary. So the left boundary is dfs left. So we're going to do root left. Then after this, so we're going to get the leaves. So that is df leaves. So we're going to apply it to root. The reason is that The root is we do not regard it as a leaf in this problem. So next we're going to get the red boundary. So let's see, red, and that's the problem logic. So afterwards we can do the return after we have boundary. So here, so let's see, boundary, and boundary. Yeah, that's it. So this forms a solution. Now let's first do a check. Non-chap has no left, so there. So let's first do this. So let's see, because we have called this function. So now let's if not root. So we're going to return empty, right? So now let's do the check. Where is line 102? Let's see. 102. If not node, or so here let's see. df left. So here is an or. Notice that the logic, right? So let's do a check. Yeah, it passes the example. Now let's look at the generic case. Yeah, it passes all the case. As we mentioned, I think we could comment out that. Let's do a check. Yes. So with that said, I guess that's about it for this problem. So in this problem, basically we used different flavors of traversal to glue the left boundary and the leaf nodes and right boundary. So here in the writing of this functions, we actually, for example, for the left boundary and the right boundary, so we exclude the leaf, right? And also when we do the df as leaves, so we exclude the possibility for the root, right? So yeah, that's about it for this video. Thank you.